Hi everyone, my name is Joris Peels, and this is another edition of 3D Printing News Unpeeled, brought to us by 3dprint.com. And today we're learning about, well, Supernova. So Supernova is it's a spin-off of BCN3D, Barcelona-based kind of like foundation that evolved into, or that spun off a 3D printing company that spun off another 3D printing company. And that company, Supernova, is a company that does VLM. And VLM is a higher viscosity SLA process that uses transparent film to make it give it a higher yield as well as having just a higher viscosity. Now, higher viscosity, of course, means that, well, that's on a scale, of course, but this compared to a lot of other SLA technologies means it's got better properties, better part properties, better heat deflection, better elastomeric properties, and now also better energetic material properties. So what the company is doing is it is founding a defense and space business unit. And the defense and space business unit, which also comes after the establishment of a Austin, Texas-based office in the States, is meant to promote the 3D printing of solid rocket motors. So solid rocket motors are in short supply right now. A lot of them are being used up in the war in Ukraine. The United States has realized that there could be some constraints in a prolonged conflict by making these solid rocket motors, and is right now doling out a ton of money to anyone who can make them reliably. Now, what some people are already doing is using material extrusion to 3D print these motors, or the fuel for these motors, in particular shapes, and then get a better result than if you would just mold it or just push the fuel in there, if you will. Now, what they propose to do is use this stereolithography technology for this. This is possible because they can print materials that have a much more higher particle load than is possible for other SLA. Now, I'm still a little bit skeptical if this will work to the extent it can work in some other material extrusion properties where these materials have already been printed successfully. But theoretically, if it does work, it could make even more geometric variability, even more finer shapes, more intricate shapes that could be improve the performance. They say that the logic here is being quick to part, developing it quicker, and scalable production. And that's the thing. If they could make this happen, then the company could very well be very, very focused on these solid rocket motors, because there are literally hundreds of millions of dollars at stake, if not billions of dollars at stake in this market, because they just can't make enough of them. And in order to defend against or to make a lot of small to medium rockets, also large rockets, it's going to be a really viable alternative. And if you could produce them quickly, like imagine if you've got an anti-tank rocket or an anti-aircraft or anti-drone type rocket. Now, by all accounts, we're going to need many, many more of these than was first thought. It's not like a country has 64 airplanes anymore, right? No, they're going to have 5,000 drones. So all of a sudden, the need for these things, these solid rocket engines, and partially also the need for solid rocket engines for space is going to explode. So this is a very, very fruitful area for them to delve into. I just don't know if it'll work, but I think it would be really interesting if somebody do this with SLA instead of just doing it with material extrusion, which has been done before. The next item is by Dcubed. That's a Munich-based space startup. They just closed a $4.4 million Series A round with Expansion Ventures, Bay BG Venture Capital, HDTGF, Ventus, Rimmed Capital, Aurelius Foundry, and others. So what they do is they want to do something really smart. They're going to make standardized components for solar and other kind of power usage for satellites and other space vehicles. At the moment, a lot of this stuff is custom. People have to make it themselves. They then get an order for a certain array. They have to make an array of 400 satellites or something. For some startup in their turn, got an order to do data mining for all the agriculture and rain data in the world, right? And they want their own satellite array. So the quicker that these satellites get built, the quicker everyone gets their money, essentially. The quicker the startup gets their data, and the quicker they can sell that data to predict rainfall in Botswana in June, the quicker then the satellite company gets its money, the quicker launch company gets its money. And now the problem is a lot of these satellites is very, very customized work. It's a lot of really assembly intensive. And what these guys hope to do in part is to make components that are kind of off the shelf, that they can make at scale, that these guys can order to accelerate their satellite production. So really useful thing. But that's not all these guys want to do, because they want to build satellite or solar arrays directly in space. So made in space, production in space. They got a €9.5 million or something amount of money additionally to this to try to demonstrate that you could build a solar array in space and print a solar array in space. So very ambitious, really showcases that there is a lot of funding money. A lot of funding money in the space race went bad already, but a lot of good money is chasing that bad money. So, maybe this will work, and maybe this will be very, very important. The next thing is news by Freemelt. So we are in a bit of an ebeam renaissance. For a long time, electron beam was kind of the hated stepchild of all the other 3D printing technologies. You didn't have the density, you didn't have the surface quality or that other technologies had, and it would then cost you more machining to get the roughness away. And then a couple things happened. So one thing that happened was people started Avia Aero initially started to figure out that you made the shape in the 3D printer and you made the part in post processing. So a lot of the properties come from post processing. If you can get it to part, in this case, a turbine, part of a turbine, to a blisk, essentially, if you get that to print very quickly in ebeam, then all the post processing steps added onto it means that you can still get an item with a lot of really interesting properties in a material that is difficult to do in powder bed fusion. And then you could make it in a still a pretty good way when compared to making it for powder bed fusion. So that caused an explosion in using e-beam, electron beam melting for space or turbo machinery, engine, all high temperature, lots and lots of applications like that. On top of that, what happened is that there was these other guys simultaneously going, oh, this is actually a little earlier, going, well, we don't mind a little surface roughness as long as we can control that surface roughness to a certain degree and maximize bone adhesion of an implant. So e-beam became really specialized in those two things. Great areas, but very, very specialistic. And it was basically just RCAM, later on GE RCAM, doing this. What then happened is a bunch of guys left GE RCAM or were fired, I don't know, one of the two, and they started Freemelt. And then later on across the pond, this was in Sweden, and across the pond in the UK, some guys started Wayland Additive. There were also some other people that have failed along the way. But there's other companies, well, like Jail out of China or out of Japan, apologies, that are also ushering in an e-beam renaissance. There are a lot of people now that are interested in part properties and creating specific microstructures or specific kind of shapes and things like that. The e-beam does really well. And one of the companies doing this is Freemelt. So in the middle of this Freemelt e-beam renaissance, what Freemelt has done is they've sold their first industrial unit. So what Freemelt until now has done is made relatively basic, but very open, very configurable kind of lab units. If you had a professor and she wanted to study a new copper alloy in e-beam or something like that, or some new intermetallic, really exotic material, then a Freemelt system would be a very cost-effective way for her to control all the variables, get all the data, have access to every single parameter and more, and to make that in a relatively simple but very open machine. Now, what Freemelt has then done is it didn't make a production system. It didn't make like a fully fledged kind of, turned on all the time. It made the eMelt ID. And the eMelt ID is meant to say, you know what? We want a machine that can go from idea to production. So it's really with that open parameter set that they're so famous for, with that kind of configure everything kind of thing, we want something that can take a company from having a very, very basic idea to configuring, figuring out a material, figuring out all sorts of things. And we're going to make that thing specifically to do it with like really unweldable, nearly unweldable metals, refractories, which would be super difficult, copper, which has been really problematic. And we're going to, pitch that at researchers and people doing really cutting edge stuff, right? And this kind of works, I guess, because until now they sold the first one. And this system, quite a bit more complex than our previous systems, quite a bit more expensive as well. They sold it to WEAREAM. WEAREAM is a Lombardy, Italy-based kind of contract research innovation cluster kind of company. And what they do is literally they get AU funding, they get together a bunch of companies to work on stuff, and they develop additive manufacturing products. So they go from like having like, I don't know, would it be an idea to have a copper antenna for, I don't know, a satellite? And then they try to, like, together with a couple of companies and some EU money, try to make it work. And so they've got one of the first of these machines. Now, this is a great thing because if these guys commercialize something, it may very well mean that they turn to Freemelt for commercializing it. And if they want something they can play around with and do all sorts of crazy settings with, then this could be a great thing as well. So I think this is absolutely fantastic and good news for the Freemelt, but also good news for the ebeam renaissance more broadly. My name is Joris Peels, and this was another edition of 3D Printing News Unpeeled. Have a